Hello, students, into the section 3.5 assessment. And if you take a look up here, we've got 3.5, 1 through 9, 12, 13, 15, 16. So it looks like I skipped 14, I skipped 17, I skipped 21. All right, so that seems pretty reasonable. So as you take a look, you got similar questions to what you had before. Place numbers in boxes to obtain the greatest quotient or the smallest quotient. Now remember, the quotient's what you get as the answer to the division problem, really. So you can kind of check yourself there. Perform operations using the bases shown. You've got bases 2, 5, and 6. We'll be doing some of that in Fivania, so I wouldn't stress that part out too much. Let's see here. What else do we have here? Rewrite as a multiplication problem. That should be all right. Find whole numbers to make it true. If it is, it's okay. Complete the fact family. Remember, division, multiplication make up a 4-fact family as well. So, like 9 times 8 gives you 72. 8 times 9 gives you 72. So a couple different ways you could do it. Perform each of the following divisions using both the repeated subtraction and the standard algorithms. Okay, so repeated subtraction, and you can do repeated subtraction with chunks of it, because honestly, the standard algorithm is a repeated subtraction. The standard algorithm, though, you have to find the exact answer. So if you're saying 8 goes into 62 and the student or you don't know how many times it goes in, you can't, in the traditional algorithm or the standard algorithm, you would not put down like 3 of them because at least 24 goes in there. Okay, so let me go ahead. What I'd like to do here is do one of these questions with the standard to kind of give you an idea of what teachers have for a while been trying to show students in order to do the standard algorithm correctly. This is a way to assist. And so some of these numbers are a little bit more challenging than others. So actually, this problem is not ideal for a standard algorithm. It's good that it has 2 digits, which I think I wanted, but let me start with A. And so as I'm doing 8 goes into 623 with the standard algorithm, I need to know, first off, I would go to the hundreds place and say, do I have enough to make 8 groups of hundreds? And the answer is no, I don't, because 600 is not enough to make 8 groups of hundreds. So I'd put a 0 in that place. The next one would be now 62 groups of 10. So basically, I've converted my hundreds into tens, and now I have 62 of them. So in my mind, even though I say 62, you'll hear me saying the word 62 tens. And that again is telling me where I would write my answer, my portion for this. So if I was a student and I was struggling with that, I want to go back to the idea of multiplication. So you can do just additions. 8 plus 8 gives you 16, especially for a student who is struggling with larger numbers. So 8 plus 8 is 16. That would be 2 groups of 8. Add another 16. Okay, each of these is 2. That's going to give you 4 groups. Now that gives me 32, right? Well, I definitely have 32 here, right? Why don't I add another 16? Each 16 is 2 of them. That gives me 48. That is now 6 of them. Maybe I can get one more group of 8 in there, which would be 56, and that would be one more for 7. So what I'm doing is I'm writing how many of these 8s are in each piece. You could write the whole table out if you wanted to, 8 times 1, 8 times 2, 8 times 3. And you notice you're adding 8 every time, forming a really beautiful arithmetic sequence. But this also works. So it's kind of a quick way if you can get there. So this, I would put a 7 here in the traditional algorithm because 7 times 8 would be 56 tens. Now, in the traditional algorithm, you would subtract as it is. I've found it easier to be thinking that this is really 56 tens, and that's why my 7 is in the tens place. So I tend to put a 0 here. In the true traditional algorithm, you would not put a 0 there. Do the subtraction, and you end up with a 6, 3. So then I can look through my table and find 6, 3. Well, maybe one more 8 would do it. That would be 6, 4. Oh, so 8 times 8 is 64, but that's too big. So that's too big. So I would put a 7 here, and I would once again get a 5, 6. The subtraction here would give me a 7. So what a fun problem, right? The answer is 77 remainder 7. So I have a feeling somebody was having a little fun when they wrote that one. No names. Let's go to this one. This is not one I probably would have put in here, but let's go with a little bit of a bigger number then. Let's do 36 divided into, what do I want to do? 2,978. So I'm going to make this bigger. Okay, and the reason I'm making it bigger is you don't often see the reason to do something like what I just showed with the eights until you see a question where you are stuck using other methods. So we're going to highlight that now. We're going to get rid of it. Here we go. So now what I would do is I would do something like this. Do I have enough thousands to make 36? No. Do I have enough hundreds to make 36? No. So now I'm into the tens, and in the problem here, I have 297 tens, and I definitely have enough to make groups of 36, but I don't know my multiplication by 36 very well. So what I do is I come over here and I usually do a couple. 36 plus 36 gives me 72. Remember, that's two of them, right? Add another 72, right? That's two more of them, gives me 144. That's two of them, right? Sorry, that's four. 2 plus 2 gives me 4, not 2. And then I'll just add another 144 on here because that's 4 of them. And now I get 288, and that's 8 of them. So I have 1, 2, 4, and 8 as a very quick way to get some progress on this question. Now, in this case, 288 works beautifully. So I'm going to put 8 groups of 10, put 288 here. And when I subtract, I end up with, looks like 10, but a -1, so 9. And I'll bring the next one down. Okay. So now I have 98. Okay, so I'm looking like a pretty good place here. I'm just going to put 72 in there because I know it goes in at least 2 times, and that would be 26. Now, I could have been wrong, but in this case, 26 is less than 36, so I'm in a good place. If I was wrong, if this came out to be 46 for some example, I would just put one more group of 36 on top. And then when I wrote my answer down, I would have written 83 because I'd have 2 plus 1. That's the scaffolding approach. Okay. So it links it in there. But in this case, I don't. So the answer here of 2978 divided by 36, the answer is 82, remainder of 26. All right. Clear that. Okay, so anyway, that's the idea there. Doop, 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 doop. Is it possible to find a whole number less than 100 that if you divide by 10 has a remainder of 4? You could find a whole sequence of those numbers, right? What are the numbers that when you divide by 10 have a remainder of 4, right? So it has to be less than 100. So if I divide by 10, I'm making groups of 10 and it has a remainder of 4. So it's 4 more than a group of 10. So as you go, you would say, that could be 4, 14, 24, 34, right? And then you say, and also the same number when you divide by 47 has a remainder of 17. Different idea. You absolutely could check and see, I wonder if anything in my first list matches the second list. Let's see here. What else do we have? What possible base is this? Oh, what a great question. So if you did this question right, what possible base would this be? And it does look like, yeah, I got to look at this. I got a feeling here, and this could be just the digital book. I can't see it in my print book, but this line right here, just so you're all on the same track, they may have this one off a little bit. I think this could just be the way they had it lined up. I believe this is what they meant to write here, just over a little bit, so that when you subtract 4 minus 3 is 1, 1 minus 1 is 0, and then you get a 2. Okay, so the 102, like all these should be shifted over a little bit place value wise. So I'm not sure what occurred there. I'll have to check the book and see if that's also in the printed book. Might just be in the digital copy. I'm not sure. Okay, so just move it over, but it's the rest of it looks like it's in a good place. So yeah, really, you're taking 2 times 1, 3, and it gets you 3, 1. So think about that. 2 times 1, 3. 2 times 3 would be 6, but you don't have 6 there. You have a 1. You have a remainder of 1. So if you have a remainder of 1, it kind of tells you what the base is. If you had 6, and you end up with a remainder of 1. It tells you how much you must be grouping by. Okay, let's see here. What else? Divided into 12 tens. Later, they're divided into this. So these are great questions because as you're doing it, you kind of have to rethink how many total students were there. They don't tell me, but I can figure it out. Then I can solve a second problem. So these are good questions. I do like these questions. Place parentheses if needed. So remember your order of operations. Remember what comes first. Remember what comes next. And then put parentheses in if you need to. So for example, if I was doing part B, 8 plus 7 would be 15. I take away 3, that gives me 12. I don't need parentheses here. So I don't need them. And it says if needed. So I don't want to just put parentheses where I don't need them. For the next one, 5 plus 6 times 3. Multiplication would come first. 6 times 3 is 18. 18 plus 5 is 23, not 33. So in the first one, I need some parentheses to put in to make sure that it is true when I do that. Let's see here. Oh, down here, what a great question, right? These are estimating questions. So if you look at this and you have the first one, right? 299 times 300, and they say, here's your target number of 90,000. That's what you estimated. So you said this is approximately 90,000. The question is the estimate too high or too low? And so when you look at this, if you think I was trying to estimate 299 times 300, I probably used 300 times 300, which is equal to 90,000. So if you take a look, my number is bigger. So 90,000 is too high. My actual number would be less than that. So I didn't have to multiply the actual exact values out to demonstrate why I would be higher or lower. Okay, awesome. And then you get the 3B. I wonder if there's anything in here that really sticks my mind. So I skipped 10 and 11. I skipped 14. I skipped 17. Mary Kay. Oh, yeah, I skipped that one. My mother sells Mary Kay, so I just can't give you that problem. Sorry about that. Yeah, it's a trauma that I'm not over yet. Let's see here. Oh, see, yeah, this problem here, they actually did it correctly. They lined that one up correctly. So maybe it was just one on the part A. Let's see here. Yeah, 20, 21. Oh, I didn't make you do 21, and that's fine. That's okay. 20, that one's more algebraic. I think I skipped it for that reason. And yeah, oh, 16. Maybe should I look at 16? This is one where students do kind of have a little bit of trouble. So I'm going to highlight 16. And so 16 says, find all the whole numbers that leave a remainder of 3 when you divide by 5. So when you're doing a problem like this, just pause for a second and say, hold on a second here. Let me take a number, any number, and I'm going to divide by 5 and see what I get. So let's just say that I take the number 21 and I divide by 5, right? Okay, well, 21, 5 goes in there 4 whole times, right? Because 4 times 5 is 20, and I get a remainder of 1. Okay, so upon division by 5, so that means 5 is my divisor, I get a remainder of 3, but you can see over here, my remainder that I got was actually 1. What that tells you, though, what you can do is say, wait a minute, I need a remainder of 3, so I need my remainder to be 2 larger, and that means that my number over here would have had to have been 2 larger as well. So I actually need the number 23. Okay. And so then if I take 23 and I say, okay, 23 divided by 5, that does have a remainder. Notice the next number that has a remainder of 3 would have to have another whole group of 5. So this 23 is 5 times 4 plus 3. The next number would be 5 times 5 plus 3. The next number would be 5 times 6 plus 3. And you get this beautiful sequence, which is 5 times whatever number you want plus 3. It's an arithmetic sequence, and your common difference, you guessed it, is 5. So you end up going up by 5. So dot, dot, dot. And it can go down by 5 as well. So 18, 13, 8, and 3. So if you want all numbers that work like that, you get this beautiful arithmetic sequence. You could also write it in set builder notation, right? It's the set of all x as long as x is equal to 5n plus 3, where n is, what do I want? I want a whole number here because it's okay if n is 0. And there it is. So this is probably the easier way to do it, this one over here, because it's so descriptive. It tells everybody all the different terms you could find. The one on the left assumes that it has to keep going in the same pattern, but you didn't say that. So there are some issues with listing the terms like this where, maybe it works that way and maybe it doesn't. Okay. Anyway, I think that's probably one that some students tend to get a little bit stuck on. Let's see here. Can I undo the highlighting? Maybe I highlight again, then it removes the highlighting. That's more highlighting. Undo the highlighting. Oh, delete highlight. Okay. All right, there we go. That did not seem to delete it. There we go. Okay. Let's see here. What computation must be done last? That's fine. Yeah. I think these seem, for the most part, I feel like these are pretty reasonable questions. I went through the part A, so I'll do math connections in my next one. All right. That's it for now. Off you go.